All right, section 21.10, preparation of esters. So we've talked about several carboxylic acid derivatives up to this point, and now we're getting to look at esters, and then next will be amides. So this is going to look familiar, I hope. We're going to have, in order to make an ester, the first way we're going to learn to make an ester is take a carboxylic acid and treat it with methanol in the presence of acid. Can you see methanol there? Treat it with methanol in the presence of acid, and bam, right? So we've seen this motif before. Let me change colors. Come here. We've seen this motif before. So in order to make our electrophile more electrophilic, we first of all protonate. Bam. Right? And there's our protonated carbonyl. Right? And so it's more attractive now to the methanol, and so the methanol comes in, bam, making a new carbon-oxygen bond, tetrahedral intermediate, this is deprotonated. We've seen this about 100 times, right? That's deprotonated. And you can guess what's going to happen, right? If we're making an ester, we're going to unprotonate, or rather protonate one of these to make it a good leaving group, right? So this is just the first part of the mechanism. The next part's on the next slide. So sure enough, we're up here, okay? Sure enough, we have this carboxyl, this hydroxyl is protonated, all right, with the acid, the acidified methanol, right, makes a good leaving group, and bam, leaving group goes, okay? And then we have to unprotonate this last guy. So, here we go, all right? Now, if you instead did this mechanism, right? We have a water molecule that left. Where did the water molecule leave? It left right here, right? The water molecule is leaving. If you took that water molecule and deprotonated this instead, that would be fine. Why is it more likely to be methanol? Why is that? Why is methanol better? And why is this okay? I guess that's another question. All right, so anyway, we've made our methanol. Now, it turns out that every one of these steps was in equilibrium, right? You saw that. Boom, boom. Right? Every one of them. And so what does that mean? That means that if we do this in a bath of methanol, we're going to tend, where are we here? If we do it with a Le Chatelier's principle, we can push things in this direction. If we do it with water, we can push things in this direction, right? Okay. So the mechanism for esterification and unesterification, which is called saponification, we're doing next section, is virtually identical. All right, so the overall Fischer esterification reaction, which I just said, is an equilibrium process where this oxygen is here, right? That's the only reason this is starred, is to show you, hey, look, this is the guy that's coming in, not just the ME. Sometimes people think that the methyl group is replacing the hydrogen, and it's not. It's the methoxy group, which is replacing the hydroxy group. Okay? So, and I answered this one. I answered this in the last slide also. How much you use Le Chatelier's principle to favor the product? Let me not say it again. I said it just a slide ago. You look at that. How would you use Le Chatelier's principle to favor, to push the reaction this way? Or conversely, how would you use Le Chatelier's principle to push it that way? Okay, is there an entropy difference which might be exploited? Another sort of puzzler. These are two key questions, I think. Key questions. The last one is a little subtle. All right, I think we're going to see one other way to make an ester, and that is not in acidic conditions, right? This is called an acid chloride, but really you can see it's an acyl chloride, right? Or alkanoyl chloride. So this is done in basic conditions, and we can make the ester like that, where the alkoxy replaces the chloride. All right, now go practice with conceptual checkpoint 21.22 and 23. Good luck.